Okay, so we're going to continue along the path towards trying to understand energy and electromagnetic radiation. Last time we mentioned what frequency was, so can you remember and tell me? Okay, so frequency is the number of wavelengths of light, in this, or electromagnetic radiation. Light really means visible light to humans anyway, but all forms of electromagnetic radiation are possible. Move like a wave, and so any frequency is the number of wavelengths of light or electromagnetic radiation that pass a point per second. Now I wanted to go back over the properties very quickly before we start getting into some of the math. So again, light or electromagnetic radiation move as a wave. They move at the speed of light. Now the speed of light, if you remember, was 3.00 times 10 to the 8th meters per second. That's really fast. Now that's in a vacuum. Light actually moves slower through air or water or anything else. But in a vacuum, it moves at that speed. Now the distance between the two peaks or two valleys is the wavelength, and we use this symbol lambda. And the number of peaks, so how many of these would say here's a point, how many of these propagate and pass its point per second is frequency. Okay. Now, here are some simple relationships. So like we said, electromagnetic radiation moves at the speed of light. We abbreviate that with the letter C. And there's a relationship between frequency, the speed of light, and wavelength. So here's a couple of the relationships, the little formulas here, which you will have if you do any worksheet or whatever. So wavelength equals the speed of light divided by frequency, and frequency equals the speed of light divided by the wavelength. Okay. Now, this is a key concept to understanding our models of the atom that we are going to be derived by scientists who are looking at atoms and looking at these specific wavelengths of light that are given out by atoms when they're hit with energy. And what they found is that only certain energy transitions were allowed. Even more fundamental, a guy named Max Planck figured out that energy comes in multiples of a uniform size packet. I know that doesn't make any sense, but it's what he's saying is that if you have a wavelength of this light, say a frequency of, I don't know, 1 times 10 to the 9th wavelengths passing a point per second or something. If you have something like that, if you have a frequency like that, it's made up of multiples of energy. Even though you got a wavelength value of energy, as you'll see, or a frequency value of energy, you're going to see that it's made up of multiples of a common factor. So quantized means that energy absorbed or emitted by atoms comes in these same size packets. It's just multiples of them, called quanta. So this is different. This means that all energy emissions or absorptions are not possible. There are only certain ones that are possible, and they have to be multiples of this small amount of energy. Now, this energy is really small, which is why it was so hard to actually realize that energy is quantized. So a quantum of energy equals this. So it's 6.6261 times 10 to the minus 34 joules per second. It's known as Planck's constant. Max Planck is the guy who figured this out, abbreviated with the letter H. So that is really small, all right? He observed matter, and he was able to do experiments to prove that all wavelengths of light are multiples of this. So that's very interesting. He also came up with this equation that the energy of any electromagnetic radiation equals Planck's constant times the frequency. Again, E is energy, H is Planck's constant, F is frequency. So this is an important equation to relate electromagnetic radiation to energy. Now, we'll go into line spectra more in the next section, that's 11.2, but every atom has a unique pattern of these energy emissions, all right? These energy emissions, they've been determined for every atom. That's why we know they're unique. We've looked at every single one, and we know exactly what the pattern you would get for an atom of a specific element. Now this observation, these unique energies of light for each atom, is critical to understanding the underlying mathematics of modern atomic theory, because any mathematical model that tries to explain what's going on inside an atom has to account for all the differences in emissions you get for all atoms. Now, I wanted to say one more thing as a sideline. We look at stars all the time, astronomers do, and we can look at stars from other galaxies for that matter if we collect light long enough and we have a good enough telescope. We can actually take that light and manipulate it so that we can see all of the little bands that correspond to all of the atoms that are, say, coming from a star that is in another galaxy. So we can actually tell, using this information of line spectra, the composition of stars in other galaxies, which is really wild. Now, we're going to go into a sample calculation. So, how could we find the energy of light in a 555 nanometer wavelength? Okay, the first thing we have to do, because everything is really in meters, is we've got to convert nanometers, okay, to meters. And you'll see I have a little chart that you'll get on the worksheet that shows the relationship, but there's 10 to the minus 9 meters per nanometer. So this is one way of setting this up. And so basically when you multiply 555 nanometers by 10 to the minus 9, you get 5.55 times 10 to the minus 7 meters. So that's the wavelength of the light in meters. Okay? Then, as you see, Planck's equation, it's energy equals Planck's constant times frequency. So this is a wavelength. So we've got to figure out what the frequency of that wave is. And we use the formula that I showed before. There's a relationship between frequency, wavelength, and the speed of light. And so by taking the speed of light and dividing it by the wavelength, which we have here, we come up with frequency. Now, do you notice it says s to the minus 1? S here is seconds, m is meters. So s to the minus 1 simply means 1 over seconds. In physics, you abbreviate that as hertz. A hertz is 1 per second. Okay, now we got to find the energy. So we've got the frequency, we got it from the wavelength, got it from nanometers to meters, and then found the frequency in hertz, and then we multiply it out. And so you can see we take our Planck's constant and we multiply it by the frequency. Now look, joules times second is in the numerator. This would be seconds in the denominator, so seconds cancel and you're left with an energy with joules. You can see that the amount of energy in one photon of light that has a wavelength of 555 nanometers is pretty small. But this is essentially how you do all these energy calculations. So you're going to have to manipulate things so you get things into frequency, and then you can use the Max Planck's equation here, energy equals Planck's constant times frequency, to find the final energy. And your final energy is going to come out in joules. Okay, that's it. Go on, work on the worksheet. All right, I did put up some unit conversions here for you, just so you can see them. And I give an example of how to convert them. There's different ways to write these. Here I wrote 1 millimeter equals 10 to the minus 3 meters. Okay, you could also write 10,000 millimeters equals 1 meter. You could write the relationship either way. Here I wrote it with millimeters, micrometers, and nanometers on the left, and the corresponding values in meters on the right. But it's just like anything else. If you've got to convert between units, all you have to do is use a fraction set up from these using the correct ones. Here, going from nanometers to meters, we put meters in the numerator, nanometers in the denominator, nanometers cancels out, and you're left with meters. So you'll end up with a reasonable value. I did put some conversion factors on the worksheet.